Hello, my name is Joe Vasta, and today we are going to look at some interesting formulas. The first thing we're taking a look at is the odd number sequence, 1, 3, 5, 7, 9, etc. A sequence is a list of numbers, and we can label each of those numbers. This is an A sub 1, sometimes called A1, and then the second term of the sequence is A2, A3, A4, etc. So the 12th term of this sequence is 23. So what we're going to look at for the odd number sequence is a recursive formula. Recursive formula, you need the term that's before to get this term, the present term. So let's take a look at an example on this. A6, for instance, so we already know A6 is 11, but if you wanted to use the formula, we get it's A5 plus 2, and you can see we just plugged a 6 in for n in this formula, so A6 equals A5 plus 2. Well, we know what A5 is. A5 is 9. 9 plus 2 is 11, and so that tells us what A6 is. So if we want to find out what A100 is using the recursive formula, that would be A100 equals A99 plus 2. But you would have to know what A99 is, and to get that you would need to know A98, etc. So a recursive formula reminds me of like stepping stones. Well, we have a different formula for the odd number sequence called the explicit formula, and that you just plug the number in there, and we don't have like other A sub this or that on the right side. So if I wanted to find out what A6 is, I plug 6 into this formula. I end up getting 2 times 6 minus 1, that's 12 minus 1, which is 11. So we want to point out the difference between an explicit formula, where you could actually find A100, that would be 200 minus 1, so A sub 100 is 199. And the recursive formula, where you use preceding terms to get the next term. Now, even though it seems like the explicit formula seems to be better, there is a time and place to do a recursive formula, and sometimes that is the more preferred formula depending on the application you're doing. Let's take a look at another sequence. This is the Fibonacci sequence. It goes 1, 1, 2, 3, etc. And some of you may have seen this sequence. How do you generate like this term here? This 13 is gotten by adding the two terms before it. So 8 plus 5 is 13, and 13 plus 8 is 21. So the recursive, well, there's the labelings F1 through F12, and these sequences go forever. The recursive formula looks like this: Fn equals Fn minus 1 plus Fn minus 2. And with the recursive formula, we're always looking for the seed, or in this case, the two seeds. Without the two seeds, we can't get started. So you can get started by finding F3 by going 1 plus 1. And that's what this formula here says. So let's take a look at our F6. We plug 6 into this recursive formula for n, and F6 is F5 plus F4. Looking above at what F5 and F4 are, well, that happens to be F5 is 5 and F4 is 3. So 5 plus 3 is 8. So F6 is 8. And that's how the recursive formula works. So if we want the 100th Fibonacci number, or F100, you'd have to add up F99 plus F98. But of course, you would need to get those, and so we'd have to go all the way using the Fibonacci numbers as stepping stones to get up to F100. Well, we have an explicit formula for the Fibonacci sequence, and here it is. This is going to surprise some of you. Wow, look at that. It has the square root of 5 in there. And so we're not going to prove this formula in this video, but what happens is if you put a 1 into this formula, even though there's square root of 5's over here, you're going to end up getting 1 for the answer. You put 2 into the formula, this thing's going to simplify and give you 1. And you put 3 into this formula, then you're going to get a 2 on the right-hand side. You put 4 into the formula, it's going to give you a 3 over here. Now that seems unbelievable. You can do this on a computer. What I'm going to do on the next slide is put 6 into this formula. So here it goes. So F6 we know is 8. So we know that F6 is 8, and we're going to plug that into the formula. F6, everywhere there's an n, and there's 2 n's over here on the right-hand side of that equation, and we put 6's there. So my next step is to do just a little algebra here. I have 2 to the 6th on the bottom, and 2 to the 6th on the bottom, so I write that. And then we just kind of separate out those parentheses. My next step, they have a common denominator. It's the same denominator, so I just write that denominator. 2 to the 6th, by the way, is 64. My next step that I'm going to do, and I'm not going to go through all the little details, I'm going to use the Binomial Theorem, multiply out 1 plus root 5, 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 1 plus root 5. And the Binomial Theorem is a quick way you can do that using Pascal's triangle. I'm not going to go into that right now, but what I got is that right there. So there's the first part. This 1 plus root 5 to the 6 gives me these 7 terms here. And then 1 minus root 5 to the 6 gives me these 7 terms here. I'm going to distribute that negative on the next step. And then I'm going to see, if you're looking at the top, you have some things with root 5's and some things without root 5's. Well, the things without root 5's, well, look, there's a 1 and a minus 1. Those are out of there. And a 75 and a minus 75. Those are out of there. 375 minus 375. 125 and a negative 125. And so I add up the top, I have like a 6 root 5 plus a 100 root 5 plus a 150 root 5. So, let's see, that gives me 256 plus another 256 root 5. That's 512 root 5 over 64 root 5. The root 5's cancel. 512 over 64, you can check this out on your own. It is 8, and that gives me the 6th Fibonacci number. So there is a disadvantage of this explicit formula. It's pretty algebraic, and the recursive formula, I could have got that 6th Fibonacci number a lot faster. But this is kind of a neat formula. So let's take a look at it a little bit more. So there's the formula, and the blue part, 1 plus root 5 over 2, that is called the golden ratio. It's an irrational number, and lots of times people use the Greek letter phi. Some people will use tau, but we're going to use phi here. And we can rewrite this really cool explicit formula using the golden ratio, and here it goes. It is phi to the n, so the blue part is phi to the n over root 5. And then actually, this right here, 1 minus root 5 over 2, that's really 1 minus phi. You can kind of verify that on your own by writing this 1 as a 2 over 2, and you can see that that's the case. And so this formula looks a lot nicer, a little more cleaned up. Let's take a look at the last slide here. 2 of the most beautiful math formulas. The first one is the one we went over right there, and this gives you the Fibonacci numbers. Another beautiful math formula that Math people will say is probably the most beautiful formula. I like both of these about the same. Is this Euler identity. E to the pi I gives you -1. And here's a list of those numbers, pi, e, phi, and what I is the square root of -1. And so I hope you enjoyed this video.